A mathematics professor was giving a tour of the university to some new students. When he got to the cafeteria, he said with a flourish, "And this is our binomial cafeteria." One of the students asked, "Is it called that because there are so many choices?" To which the professor replied, "No, it's because you should buy no meal here." Get it? Speaking of which, I got a bonus. I don't know if you can see it, but my t-shirt says, there are two types of people: those who can extrapolate conclusions from incomplete data. Get it? I don't know if you get it or not. Anyways, let's get back to our lesson. So what we're going to look at is the binomial model. We're going to start with an example. 30% of M&Ms are covered in speckles and mixed randomly with normal candies. You buy a very large bag and remove 4 candies one at a time looking for speckles. Does the probability that a candy is speckled change if you draw only a few M&Ms? Well, I mean, honestly, I don't know if it really matters if you draw from the whole bag or not, but definitely if we do a small percentage. But I'm going to say that actually when they manufactured it, that's where the 30% M&Ms were set. And before they filled the bag, every M&M that went in there had a 30% chance of being speckled. So the probability doesn't change for any of the individual M&Ms. Now, if we are doing things like, say, using a card deck or other stuff, when we're sampling without replacement, the probability stays the same or good enough if we take less than 10% of the population. Just an FYI there, and we'll revisit that. So don't worry. And you're probably going, where'd you get 10% from? There's a lot of math behind it. We don't have time today. All right. So you've seen these tree diagrams before, right? So we're interested in determining the probability that when drawing 4 candies that 2 are speckled. So that means I have 2 to the 4th branches, 16 branches, and I've gone through the trouble of drawing them all here and even putting them on your notes so you don't have to draw them. So the only way we can figure this out is with a tree diagram right now, all right? Let's first look at the probability that the first 2 candies are the only ones speckled. So what I would want to do is I'd have 0.3 of the probability of speckled times probability of speckled times probability of not speckled times the probability of not speckled. And when I put that all in, I get 0.0441. By the way, I went ahead and put in all the speckled probabilities. Remember that on the bottom here, any of these that match up, pair, or if you have more branches, they all have to add up to 1. So this is automatically 0.7. So what's the probability the last 2 candies are the only ones speckled? Well, it's the same idea, right? I just do 0.7 times 0.7 times 0.3 times 0.3, and I get 0.0441. So 4% probability, 4.4%. Were these probabilities the same? Why or why not? Yes, they were, because all I did, it's the same number of speckled candies and the same number of unspeckled candies. And so all I changed was what order I did that. And order doesn't matter when we multiply. Remember the commutative property where you can switch things? Yes. So when the probability of success, P, does not change from one trial to the next, we only have 2 outcomes. We call these Bernoulli trials. Oops. So when the probability of success, P, and that's a little p, does not change from one trial to the next, in this case, P was the probability of getting a speckled M&M. And we only have 2 outcomes. In this case, we're getting either a speckled M&M or we're not getting a speckled M&M. We call these Bernoulli trials. So what is the probability of drawing 2 speckled M&Ms regardless of order? Note the number of successes, X, is 2. The probability of each success, P, is 0.3. And the number of trials, N, is 4. All right. Well, what I could do, because I have my tree diagram here, is I could just go through and highlight all of them, right? Say everyone with 2 successes, and there are 6 outcomes. So I can just go 6 times 0.3 squared times 0.7 squared, which gives me 0.264. All right. Well, if we change a problem of 2, drawing 2 speckled candies, to drawing 2 out of 5, then I would have 2 to the 5th. I would have 32 branches. That's too much work for me to do. I don't want to have to draw a tree diagram every time I'm doing a binomial distribution. So is there a faster way to figure out how many paths lead to my specified number of successes? Well, the number of paths that give the two speckled M&Ms is called the binomial coefficient. And we often see it in the form of Pascal's triangle. I know if I have any math nerds here, you've probably seen this before. And also when you studied in maybe algebra or pre-cal, when you did binomial expansions, these numbers might look kind of familiar, like x squared plus 2x plus 1, x cubed plus 3x squared plus 3x plus 1. So you've seen this before. Well, so what we can do is these actually give binomial coefficients, right? So for this one, I have the 6 because there are 4 things to choose from, and I have not 0, not 1, but 2 are speckled. That's how we get the 6 off of the triangle. So I could just say, all right, so I'll just look up my binomial coefficient for n and x, and then do p to the x, so that's the probability of a speckled, times to the power of how many speckleds I have, and then the complement to the leftovers, whatever's left over, right? But here's the problem. Okay, well, that works pretty well up to 8, and I could even probably do 9 or 10, keep a little printout with me. But what if I had 20? So there are counting methods that can do this, so we don't need Pascal's triangle, although it's cool to see. Okay, so we just learned permutations. Maybe that will give us our binomial coefficient. So I'm going to put in n is 4 and x is 2, all right? And let's see how that works. So I'm putting 4 and I'm putting 2 and I'm calculating NPR. I got 12. Wait a second, but we want 6. Why aren't we getting the same number? Well, permutations is when order matters and we can tell a difference from one position to the next. But let's say I have the 2 speckled M&Ms in the first 2 positions. What I'm trying to say here is if I switch the M&Ms, they're still both 2 speckled in the first 2 positions. Those look the same to me. All right? So when we say we want 2 speckled out of 4 M&Ms, we don't care which speckled we get first. So the order of the actual things, the successes, doesn't really matter because they're all successes. Okay, so the types of problems where order doesn't matter, those counting problems are called combinations. All right, so how do we take that permutation formula and adjust it in general? So now I have the combination formula, NCX is n factorial over n minus x factorial. That's like the permutation formula, but I divide by the number of ways I can arrange the x items. All right, so you can see, let's go ahead and calculate it. You put in, we're doing 4 and 2, and instead of doing permutation, click on combination, and voila, there we go. We have the number of ways to choose 4 things. Now, you're probably thinking, oh my gosh, Mrs. Overman, this is a lot to do, right? I'm doing all this. Well, here's why you're doing it. You're doing it so you can avoid writing a tree with 2 to the n branches, all right? Because it goes 2, 4, 8, 16, 32. It just doubles every time. If you have 10 things you're choosing from, that's 2 to the 10th or 1,024 branches. Way easier to figure out the binomial coefficient. All right, by the way, on your math chart, you're probably not going to see NCX. Instead, you're going to see that notation, n over x in parentheses. Please don't confuse it for a fraction. It is NCX. How many combinations when you have n things to choose from and you take x. All right, so this brings us finally to the binomial model, which gives you the probability of exactly x successes in n trials. And here's the formula. And that's what it looks like on your formula chart, where p, the little p there, is the success in one trial. It's like the 0.3 in our example with the M&Ms. Failure would be the complement of that, or 1 minus p. You might occasionally hear me call it q, because honestly, when I first did it, we just called it q. But a lot of times it's the same thing as 1 minus p. So if anything, we have too many symbols sometimes, I think. So when can we use the binomial model? First of all, we need it to be binary, which means only 2 outcomes, either success or failure every time, right? Has to be independent. on those branches, remember I just said 0.3 to the second. That means 0.3 has to, the probability of the M&M being speckled on the next one can't be affected if I drew a speckled M&M on the first one. All right. If you're doing no replacement, don't forget to check the 10% condition. All right. And so BINS is our model for remembering the conditions on this. N stands for the number of trials. There needs to be a fixed number of trials. Otherwise, we don't know what N is and we can't do combinations. And the probability has to be the same. So I want this formula. I don't need to be doing different probabilities all up here. If I'm doing that, I might as well do a tree diagram. So the probability does not change from one trial to the next. All right. So let's go ahead and practice just seeing if certain problems qualify for the binomial model. So that's part of the skill set you need to learn. You have to be able to tell the problems apart. So let's say we're going to look at M&Ms from Cleveland, okay? And this is the actual distribution for the Cleveland, Ohio factory, all right? And I give you one package of 55 M&Ms as your sample. And you count how many M&Ms of each color are in the bag, all right? Can we use the binomial model? Well, it's not binary. I didn't say orange or not orange. I said count all of them. So we can't do that, right? Are they independent? Sure, the color of the first M&M doesn't affect the second. Are the number of trials fixed? Yeah, they're only 55 M&Ms. Do they have the same probabilities? Yeah, because the bag that comes from the production line is definitely not using more than 10% of the M&Ms. But because that first one, the binary, is not met, we cannot use a binomial model for this problem. Okay. Let's say you decide to count how many M&Ms it takes until you get an orange M&M from your package. All right, is that binary? Yeah, either my M&M is orange or it's not orange. Is it independent? Well, I'll get to that one in a second. Is it a fixed number of trials? No, we don't know how many M&Ms we'll have to draw to get an orange. So here's the problem that we have right here. Is it the same probability? Yes. Each M&M that went into the package had a 20.5% chance of being orange, but it's not the binomial model. But the M&Ms were independent. I mentioned that earlier. So if you're trying to say, ooh, how many times till I get, that's not a binomial model. You need a fixed number of trials. How about you just count how many are orange in the package? All right. Is it binary? Yes. All right. And I'm going to go in a different order again. Are the probabilities the same? Honestly, these are very related. Same probability and independent. For me, I would just kind of lump them together. But we're going to use bins, so let's go for it. All right. Yeah, P is 0.205 from one M&M to the next for it being orange. Okay. We do have a fixed number of trials. And we can use a binomial model because it's also independent. The color of the first M&M doesn't affect the color of the second M&M. All those M&Ms that went into that package, every one of them had a 20.5% chance of being orange. So let's say you get a deck of 52 cards with 13 hearts and you draw 5 cards without replacement and count how many hearts you get. All right, so binary. Sure, it's either hearts or not heart, right? And we're going to do independent. No, the probability of drawing your probability of drawing a heart on the second card goes down if you draw one on the first. You can probably strike that second probability. All right. Are the number of trials fixed? Yes. Trial is draw a card and you're only drawing 5. Is it the same probability? No. Let me go, which means we already know it's not the binomial model. There are not independent trials, and the probability does not stay the same. So here I can say, hey, look, probability of a heart on the first card is 13 out of 52, right? But what's the probability the second card is a heart, given the first one is a heart? Well, I only have 12 hearts left out of 51. So here we're dealing with more than 10% of our population. We're affecting it, and the probabilities do change. All right. So let's go ahead and practice with a case that is definitely well, let's make sure it's a binomial distribution. You've got a 5-question multiple choice quiz. You haven't studied and don't know any of the answers, all right? Each question has 4 choices with only 1 correct answer. We want to determine the probability of getting a certain number of questions correct. So what is a trial? What is N? Trial is answering a question, all right? And there you're going to do it 5 times. What is a successful outcome, and what is its probability P? Outcome is the right answer on a question. Probability you get the correct answer just guessing on a question is 0.25. What is the random variable X? X is the number of correct answers after 5 attempts. So what's the sample space? What are my possible outcomes for X? Well, you could get 0, 1, 2, 3, 4, or 5 answers correct on this quiz. All right? So anytime you're doing a binomial distribution problem, you want to identify N, you want to identify P, you want to identify X, and it sure helps to write the sample space for X, all right? So calculate the probability of getting 0 questions correct. So let me write down my N, P, and X, because those are very important. Now, X can change from question to question. N and P are usually the same for one scenario, okay? So that X number is going to change as we do different problems, all right? So I'm going to go ahead and use the formula, and I'm going to put in 5 and 0 for combinations for my coefficient, and then 0.25 to the 0 because we're getting 0 questions correct. Very unlucky kid here, all right? And then we do 1 minus P, which is 0.25, 1 minus 0.75 to the 5th. And what do we get? We get 0.2373. So we would expect about 24% of the kids to get nothing right if they were guessing on a 5-question multiple choice test. All right. So what's the probability of getting them all correct? All right. So N is 5, P is 0.25. See, those didn't change, but X did. All right. So we're going to just substitute in those numbers. And by the way, a combination of 5 choose 0. If you have 5 to choose from and you pick 0, how many ways are there to do that? Just 1. That makes sense, right? If you have 5 things to choose from and you have to take all 5, there's only one way to do that one too. And so when you go 0.25 to the 5th, basically you get this crazy number, 9.765625 E minus 4 if you're doing it on your calculator, all right? Well, what does that mean? That -4, this is scientific notation, and that -4 means move the decimal 4 spaces to the left. If it's a positive, you move it to the right. If it's a negative, you move it to the left. All right, so you're making it smaller. You're dividing by 10 to the minus, or well, you're dividing by 10 to the 4, which is why it's negative. All right, because you could say multiply by 10 to the 4, and if you divide by 10 to the 4 and then move it up to the multiply, it becomes negative exponent. Just an FYI. All right, so basically what I can do is I can write the number down, throw a bunch of zeros in front of it, and just move it 4 spaces to get my answer. All right, and you will be running into answers like this, just an FYI. All right, so pay attention what decimal place we say. Remember, that's the tenths, that's the hundredths, that's the thousandths, 10,000ths, hundreds, thousandths. It always increases by a power of 10. Or depending how you look at it. All right, so let's calculate the probability that one question is correct. All right, we're definitely going to need the binomial coefficient here. So N and P are the same. X is now 1. So I have 5 combination 1. 0.25 to the 1, 0.75 to the 4. 5 combination 1, if I have 5 things to choose from and I only take 1, that's only 5 things. So I'd have 5 times 0.25 to the 1, 0.75 to the 4. By the way, I'm very good at doing combinations in my head. You are not expected to necessarily do combinations in your head, but the more comfortable you are with it, there are certain shortcuts. If you want to bug me, I can show you how to do it. The more comfortable you are, the more you know, okay, this all makes sense. It's great for checking things. Now let's do 2 questions correct. So the only thing changing is X is now 2. And then I substitute in my formula. And of course, the exponents, don't get me wrong, this is not the only thing changing in the probability formula. These exponents are also changing because I need 2 correct. And there was only a 0.25 chance of doing that. And I had 3 incorrect. And this just tells me the number of different ways I can get 2 correct. And yes, I can do this one in my head. It's should be 10. All right. So 5 choosing two things should be 10. All right. So we multiply all this out, probably using your calculator, right? And we get 0.2637. By the way, I will post a calculator instructions on how to do combinations and permutations as well, and the binomial distribution. All right. So let's do 3 questions correct. Same idea. Oh, let me go ahead and use the notation on your math chart. So you can see the coefficient this way, or you can see it this way. Either one is fine. You should know what both means. This is not 5/3, not 5/3. The answer for this one is also 10, by the way. All right. So when I multiply all this out, I get 0.0879. Then finally, 4 things. And so there's 5, choose 4, right? And we get 0.0146. Now, if we did a good job and we put all these numbers in our table, right? There they are. Then we check it. Do they all add up to 1? They do. Yay! We didn't make any mistakes. And then we can actually draw a graph of the distribution, all right? And if you had the random variables tool, remember the discrete random variables on Staplet, you could put these in and draw your distribution using that. I'm actually using another tool that I like here. All right, so the most common outcome, by the way, just looking at the distribution, is they would get 1 answer correct. And if I were describing this further, I'd say, this looks a little skewed to the right, which means these are more outliers, all right? And look at that. There's only a 0.1% chance of guessing 5 questions correct if there are 4 answer choices. Wow. Well, okay. So how about GeoGebra? Well, here's the tool. So we want to make sure the drop down shows binomial. So this here is a magnification of that because I know that's a little small. So yes, there is a Staplet tool, but believe it or not, I like the GeoGebra tool better, and you'll see why. All right. So make sure the drop down shows binomial, because this tool, if you go there, you can actually also do normal distributions, and I can show that to you. For N, put in the total number of trials, attempts or trials. For P, put in the probability of success. So in this case, we just have 0.5. And it can also calculate probabilities for multiple values of X. And I'm going to show you how to do that. Staplet also has a great tool for binomial probabilities. Honestly, I like either one of these better than the calculator because you have the graphical image, so it's going to help you understand it better. So if you're doing Staplet, first of all, enter N and P into the binomial distribution part up here, and I'll show you that in a sec. Then you click on Plot Distribution, and it can also calculate probabilities. So I'll show you how to go through that. So here we're putting in 50, it was 20, and we're doing 0.5. So it's the same distribution we had in the GeoGebra example. And here's a cool thing. You can actually click through, and it will show the probability for each of the values right there. I was pointing at the wrong spot, right there. So you can actually do that. And it looks like it goes out to the 10,000th place. So that's not too bad. And if you look underneath, I know you can't really see it too well, you can actually say between 2 values as well. But there's a reason I prefer the GeoGebra when it comes to the between values. First of all, this doesn't have the table, which you're about to see. And you can actually really, well, I guess you could put it, if it should shade it, or it'll highlight the between values. So that's not too bad either. So they're both good options. Use what you like. All right. So now you're taking a 10-question multiple choice test. So it's even harder with 5 answers for each. Can you imagine if we did the tree for that? 1,024 outcomes. All right. So we're going to complete the probability distribution where X is the number of answers you get correct. All right. So N, P, and X. Well, X is going to depend on what we're looking at, but N and P, that's the same for this scenario. N is 10 because there are 10 questions. P is 1/5 or 0.20. All right. My possible values for X will vary depending on what the question is, right? So it could be anywhere from 0 to 10 questions correct. When you're first doing these binomial distributions, I recommend writing out the whole sample space. By the way, I'm going to show you the quick TI-84 notation. It's Binomial PDF, and I have instructions on the website how to do the TI-84 for binomial distributions. Okay. All right. So we have on the TI-84, when you want to find the probability that x is a number, you pick the binomial PDF function, which should be second distribution like we did normal distribution. And then you put in your n. It's going to prompt you for n, for p, and for x. If you have a really old calculator, it's just going to have a blank there, and then you have to know what order they go in. All right, so I'm going to show you the calculator notation just so you can see it for those of you using the TI-84s. So if I want the probability of 0, I would do binomial PDF of n equals 10, p equals 0.20, and x equals 0. And my calculator would spit out 0.1074. Now, you're probably going, wait a second, I don't know how to do it. Hold your horses. It's fine. It's just fine. All right, same thing if I want to know the probability that x is 1. All right, but there are better ways for doing this. We could use GeoGebra. So let me show you how the GeoGebra works, okay? So it can be a little wonky because you put in 10 and it like slides down on you, and it's fine. It's just fine. If you start typing in 10, it'll go to the right spot. And then see, it slides down on you again when you put in the 0.2, but it's fine. It's just fine. All right. So the really cool thing is, look at that. I can actually pick ranges like what I want x to be. In this case, it's saying the probability of x is 0. And all that means is not necessarily that it's exactly 0, but it's so small, who knows what that exponent is. And actually, I can show you how big the 0 is for getting 9 right. And it spits out all of the values listed all pretty. Now, if you're using the Statlet and you hover over the bars, it will also tell you the percents, and you saw you could click through them. I just like having them all in one table. By the way, both of these applets give you the mean and the standard deviation, which we will be going over next lesson and how that applies. Okay, so I went ahead and filled out the table using the GeoGebra, all right? And let's go ahead and calculate that probability of 9. So basically, it's a combination of 10, 9. So my binomial coefficient is, I have 10 to choose from. I'm taking 9. And how many ways can I do that, right? Which, by the way, is 10. All right. So 0.2 to the 9th times, because we're going to get 9 correct and just 1 wrong, is 4.096 times 10 to the minus 6. So it's not exactly 0, but it's pretty darn close. And basically, if I put in a bunch of zeros in front of this number and move the decimal over 6 places, and that's about right, then this is a number. So this is why it doesn't it will not show up on the Statlet as a number this small. Statlet kind of, and GeoGebra, both of them tend to chop things off right here at the 10,000ths place. All right, now let's go ahead and describe the distribution. So this one I did pull from Statlet, and you can see right here, it looks a little skewed right to me, all right, and unimodal. That's how I would describe it. The most common was probably 2. I could probably calculate the medians. So right here, I can see that this is 36, 37%, which means that my median is 2 questions correct. Which, does that make sense? Yeah, I got a 1 in 5 chance of guessing it right, and there are 10 of them. So that actually makes sense. All right. So let's go ahead and we have this distribution, and I went ahead and I just put it in the GeoGebra so I can see my pretty table, all right? If I ask you what is the probability that a student gets at least 7 questions correct, that does not mean they get exactly 7 and only 7 questions correct. What does that mean? It means they get 7, 8, 9, or 10 correct, all right? So that is my sample space. Now, if I were to add up all these numbers, I would get 0.0009, okay? What is the probability that a student gets at most 7 questions correct? Well, that means that my sample space is 0 to 10, but I'm only interested in the outcomes from 0 to 7. So I could add up all of these, and I would get 0.9999. Okay. What is the probability that a student gets less than 7 questions correct? Notice how at most 7 and less than 7 are not the same. Less than 7 cannot include 7. And so my sample space, the values I'm interested in is 0, 1, 2, 3, 4, 5, 6. So I would add up all these numbers to get this answer. Finally, what is the probability that a student gets greater than 7 questions correct? Well, that would be getting 8, 9, or 10, all right? And if I add up those numbers, here's what I get. Now, let me show you why I love the GeoGebra, all right? I can actually scroll through here. So there's 7, right? There's a little arrow. You can actually click it. And I go, oh, there's 7 through 10. There's my answer, 0.0009. I don't even have to add them up. It does it for me. And then I can say, okay, I want to do the 1 through 7. There we go, 0.999. Now I want to do the 1 through 6. So let me just slide that 7 slider down 1. There we go, 0.9991. And it even shades the outcomes for you. So it's beautiful. And then finally 8, 9, and 10, which look non-existent on our graph compared to everything else. Make sure I go to 8. And you can see that I have a very tiny 0.0001% chance. Now, if on the calculator, there's also a CDF function. And again, I have a video just for the calculator, but it doesn't hurt to show it to you here either. So if I'm trying to find the probability, the CDF function will give you the probability from 0 to 6. So it only does a less than. See right here, that left bracket? I can actually say less than probability. But honestly, it's so easy to move the arrows, I don't even mess with it. But the calculator is like table A. It only does probabilities up to a certain point. So if I wanted probabilities, we'll pick an easy one, this one right here. Here, I want the situations where x is from 0 to 7. Well, the calculator function is binom CDF, not to be confused with PDF. C is cumulative, starting at 0 up till your value. Then I put in n is 10, p is 0.2, and x is 7, and I'll get this answer. Let's do another left-sided one. So this is another one where I'm interested in that, except instead of 7, I only go up to 6, and that will give me the right answer. What about these right-sided ones, this 8, 9, 10, and this 7, 8, 9, 10? Well, that's just the complement. This one right here is the complement of that one. So I could just say 1 minus binom CDF of those 6 there. I don't want those 6. All right, so you take that away. And the same thing here for this one. I want to take binom CDF of x is 7. And that's it.